Hello, welcome to this video on analyzing RTL simulation. In this video, you will learn how to compile your IP design to RTL simulations and how to analyzing your simulation waveform. Your IP design can be compiled to simulation with the XS simulation flag. The compiler links your C++ testbench with an RTL compiled version of your device code that runs in an RTL simulator. An executable is produced in the end. Signals of your design simulation can be logged and viewed later. Now let's look at the example. Okay, we are back to the same vector add example from before. We have already ran CMake for build artifacts. We can run make target the simulator. On Windows, use nmake instead. The compilation generates an executable that we can run, much like emulation. Simulation can often take a while to run. As we can see, the simulation returns correctly.
After you've compiled for simulation and ran the resulting executable, you can review the waveform in ModelSim. You'll find a view_waveforms.sh script, or alternatively a view_waveforms.cmd script for Windows, located inside the .prj directory of your compile. This script will open the vsim.wlf file and take you to the correct level of the waveform to view the I/O for your kernel. So let's open that up now. Once ModelSim opens, you can right-click on Device Image IP in this left side panel and select Add Wave New. This will open the waveforms for our vector add kernel. Then we can minimize the left panels and open up these names. You can click on this button here to focus only the relevant part of the name. The first thing to notice is the invocation interface of our kernel. Since we did not specify otherwise, our kernel has its control signals and arguments passed in through an agent interface. The signals that begin with CSR ring root AVS contain the CSR interactions responsible for writing input memory pointers and kernel arguments, as well as setting the start bit. Let's open up the register map summary file for this kernel, also located within the .prj directory. It'll have a name similar to this, containing the name of your kernel and ending in register_map.hpb. So here we see the register map for our vector add kernel. We see the addresses for the start bit, as well as our kernel arguments, including the 3 USM pointers. Note that the addresses in this header file are given for 8-bit bytes, whereas the simulation waveform will display addresses for 64-bit words. Therefore, we need to right-shift the addresses in this header file by 3 bits to match up with the addresses in ModelSim. So these are the updated addresses that we will see in ModelSim. Back in ModelSim, we can click on the CSR ring root AVS write and use these buttons at the top to navigate between the transitions in the signal. Here we can zoom out a bit and we can see the various writes occurring to the CSR when the write signal is high. Furthermore, you can see the address and the data being written. So in particular, let's take a look at the writes to addresses 0f, 10, and 11. These correspond to the 3 input pointers for A, B, and C, respectively. We can see that there are 2 writes to each of these addresses, corresponding to the lower and upper bits of each pointer. We can look at the byte enable signal to determine whether we're writing the lower or upper bits. And we can look at the write data signal to see the data being written. We can also see the write to address 12 with the value 100 or 256 in decimal. This corresponds to the input len on our kernel, where we passed in the vector size. Finally, we see the write to address 0, which corresponds to setting the start bit. Now, if we had configured our kernel to use a streaming invocation interface, you would instead see the start and done handshaking interfaces and kernel arguments appear in the simulation waveform, like this. The next thing to notice is the signals that begin with AVM. These are the Avalon host transactions where our kernel is getting input from host interfaces and writing output to host interfaces. You can see that when the read signal is high, this corresponds to a read from the host interface. We can see the address from which we are reading and the data that's being read when the read data valid signal is high. Similarly, we can see that when the write signal is high, this corresponds to a write to the host interface. And again, we can see the address and data corresponding to the write. If we instead used host pipes to stream data in and out of our kernel, we would need to open up this left side panel again and go under device image IP and select the kernel that you're interested in. So here, we look for the one that has our simple vector add in the name, and we would do the same as before and click Add Wave New. That will open up this panel here, and we can see the various pipe interfaces appear in the waveform, including the corresponding ready, data, and valid signals for each pipe. So here, we can see a read from pipe A when the read valid and read ready signals are high, and we can also see the data being read. And similarly, up here, we can see a write to pipe C when the write valid and write ready signals are both high. And again, we can see the data being written. And that concludes this section on how to view the simulation waveforms. We went over how to open the waveform in ModelSim and where to see the invocation and data interfaces of our kernel.